Hello, everybody. This is Professor Ma, and this is the sections on volume and particularly on the solid of revolutions. Okay. Uh, we had from previous sections that if we integrate the cross-sectional length, the definite integral of cross-sectional length is the area, total area. So in particular, the formula looks like this, and that in this part I can interpret as the length times a very little small amount dx. And then of course what I have is this area of this thin line segments. Then I'm going to add up all these line segments on one end to the other. And by fundamental theorem of calculus, this becomes the integral of cross-sectional length. Now we're going to do the same thing for volumes. That is, we're going to look at suppose I know the cross-sectional area of a solid. I was solid over here, V. I want to find the volume of the solid. Suppose I know the cross-sectional area of X. X go from A to B. Here's X. Okay, A to B. And suppose I know the cross-sectional area, and I take AX times DX. What's delta X? A small amount of X. And then I get a very thin slice of the volume, but it's a volume. And it's a cylinder. Basically, the volume of a cylinder is, I take the area of this, A, multiplied by the height. In this case, the height is delta X or dx. Okay. So I get this very thin slice, and then I call that volume dV. Of course, for the entire volume of these solids, I want to add up all the dV and letting dx go to 0, thinner slice. Then the fundamental theorem says, oh, that the answer for that, you just integrate ax dx from one end A to B. Okay, so that's a main theorem for these sections. Okay, before we start, we want to remind you about extracting distance. Okay. We did that from previous before. Horizontally, the distance is always right minus left. Vertically, it's always distance over the height minus low, the coordinates. Okay, and this is examples of how you can extract the distance from horizontal or vertical distance if I know the coordinates of the 3 points. Okay, and in particular, if I have a equation, if I want to, given an x, I want to find the height of the point on the equation at x, then I need to find the y coordinate. Then I want to express y as f of x. But if I want to find the horizontal distance, then I need to express x as formula in y. Okay, and here is example. Okay, if I want to find a vertical distance, I want y in f of x. So I need to solve for y. And this one is a square root, and so I want a positive one because that's what the condition says. Y has to be positive. Therefore, it must be the square root of positive square root. Okay. And then horizontal, I solve for the x in terms of y. And that's just a linear problems. Move the y divided by 2. And that's the distance from the point to 0. Okay. Well, let me phrase that a little better. This minus 0, okay, is going to be because at that point the x distance is 0, x is 0, so that will be the horizontal distance. Here's another example. Because these two curves interchange, so on the right hand side, if I want to measure the distance h2, the right-hand points will be this curve right here. will be x equal to, remember these things I want to solve, I have to express x in terms of y. So I need to solve for this one for the x, then subtract solving for this one for x. Okay. So h1, did it the other way around first. In particular, if I want to solve for the horizontal distance, I want the x coordinate of this point in terms of y, at a high y, and subtract the x coordinate at that point. But if I want to find this distance h2, it's the other way around. The right hand x coordinate minus the left hand x coordinate. For the vertical distance, you can see these. For the left hand side is the top curve is square root of 2x, square root of 2x plus 4, subtract the y coordinate 2x minus 3. Oops. And the v2, the height on the other side is switched around. Okay, so this is an important thing we're going to keep track of as we go on. And another thing we're going to do is we're going to spin lines around, and I will come back to this and then jump to the volume first, and then we come back to the solid revolution. We'll look at the spinning. Now, if I want to calculate the volume of a solid, so again, I take my tape measures and measure from one end to the other end, and then I suppose I can find the cross-sectional area of these solids as x goes from A to B, slice through. And if that's possible, then I can formulate the formula for how to calculate the volume. So here we go. We approximate by first partition the solid using a partition A to B into x1, x2 into little each sub interval. And for each interval, we're going to select a point. And again, if you like, just select the endpoints. Okay, xi will be just select as xi, and the next point is x. Just select the right hand points if you want to. Okay. And suppose the length of the subinterval is delta x. Then, since I know the cross-sectional area, if I slice it at xi, suppose xi star O, I know how big the area is. That's the assumption that I slice, the cross-sectional area is known. So I take that slice, I multiply by the thickness, delta x, and that gives me the volume of that particular slice of volume, okay? So the cross-section, so if I put it horizontally in the picture, so this is here a cross-sectional area, and delta x is the partitions, the length of each subinterval, then this is volume, what I call V sub I, or delta V, dV. Okay. Of course, now I want to add up all the volumes. And so this is what I call dV in the beginning. So if I go to the home screen, and these are the individual slices. The volume of individual dV are the individual slice of the disks, if you like. And I add them up. Okay, I add them up according to what? Let delta x go to 0. Okay. And as delta x go to 0, then fundamental theorem of calculus say, oh, these additions turns into definite integral, and the delta x become dx. Okay, so now we have therefore the volumes formula for the volume of a solid. The volume is the definite integral of the cross-sectional area. That's the cross-sectional area. Cross area. Okay. The areas is the integral of length. The volume is integral of area. cross-sectional area. This is also known as the Cavalieri principle, and we're going to talk about that in the next section. Now, so what's the game plan? Well, how do we find out volume of things? Then in order to do that, I need to know the cross-sectional area. So that when you give me a solid, I need to know that if I slice it in certain manner and the exposed area, I know exactly how to calculate that. And what type of shapes that I can do that? Well, one class of shapes of solid can do that are the solid of revolutions, of spinning. Okay. So let's go back and go back to do the spinning. Okay. Suppose I have an axles, vertical axle. Suppose I think of this on the paper. I have a horizontal line like this. So and this is an axle, and I have a line like this, and I'm going to spin this line, orbit this line around these axles. Okay. As it spins around, it forms a disc, a washer, a ring. You will hear all this name. Sorry, not a disc, a ring of washers. And it's easy to calculate the area of this ring is pi big R squared minus a little inner radius R squared. Okay. Now, if the line touches, if the line touches the axle as it spins, then it spins into a disk, a circle. Then the area of this disk is pi R squared. Okay. Now, if the line hits again the axle, if the line starts horizontal like this during the spinning, your line is vertical parallel to the axle, and it orbits and spin. And then what you form, it's going to form a cylinder. Okay, and you can figure out the area of these cylinders. Okay, it's going to be the 2 pi times the radius times the height, the length. Okay, the area of the band around as it spins in space. Remember, we try to keep track of the cross-section area, so we need this area. What happens if the line is tilted like this? And it is doing orbitings, goes around like this, spins around, and if that happens, then what we have is a rostrum. It forms a surface, okay, and that has its own surface area. Is given by this formula. Okay, now from here we're going to look at the solid by spinning things. So let's go back to here. Now we're going from solid. So again, remember we try to find the volumes, and in order to try to calculate volume, I need to know cross-sectional area and what type of solids I can calculate cross-sectional area by spinning things. Like what? Here we have a template, that is a plate. Okay, a basic shape of plate. And now we're going to do things with these plates. In this case, we're going to, here is the axle, and I have a triangular plate. I'm going to spin the triangular plates around the vertical axles, and what it finish up is a cone. Okay, so if I follow every line in the plate, I can, for instance, if I follow a horizontal line in this shape, then what it does is it will spin into this particular line will spin into a cross-sectional area. That's how we get our hands on that formula of the cross-sectional area. Suppose the shape is away from the axle spinning. Then you have this empty space in between. So as it orbits around this triangle shape, orbits around this axle, it forms a solid. Kind of how to describe it is kind of like a cake with a middle. It's a cone with the middle part drilled out of it. Okay, it's, if you like, this is a cone, but with this part you take a drill, you cut a hole into it. Okay, so So these are the solids we're going to extract the formula. Okay, now for us, we're going to first have, what are the templates? Well, one type of templates is I take a function, positive function f of x from a to b, and I take these entire things as a template that I'm going to spin it around the x-axis. Okay, if I do that, in this case, I get these things look like a base. Okay, about what's the volume of this base? Well, all I have to do is say it's going to be integral a to b of, I'm going to slice it into a very thin slice of dv. But each one is going to be, well, what's the cross-sectional area? Okay, what is, if I slice the x, okay, it got to be perpendicular with, the axle of spinning is this way, we're spinning this way, so the circle is formed by cutting perpendicular to the axle. It's very important. Okay. So at x, what I have is a disk of radius f of x. F of x is the height. So that's going to be spin around the x-axis. Hence, that disk is pi r squared, is pi f of x squared. So hence, I integrate these times dx from a to b. So this is the a disk shape. So that is, if we slice through everything is a disk, that is, if we cut perpendicular to the axle of spin of the rotations. Here's another example. Here's an example from 0 to 2. If I spin this around the x-axis, okay, I mean really fast, and then if you ever see a machine, the lathe machine, then you form these shapes, and then the radius is square root of x, and pi r squared, or the cross-sectional areas pi root x squared, so it's pi x, and all I have to do is integrate from 0 to 2, and that's the volume. Okay. Now we're going to spin this away from the axles. Okay, that means there's a spacing between. Then the shapes, the cross-sectional area is going to be a ring like this, or a washer. So I have to keep track in these shapes. As I spin, I have to keep track of two radius. Like for instance, in this particular one, I have to track all the way out there to the outside. What's a big radius? And then there's a hole in the middle, that little radius that I drill out. I have to keep track of these two distances. And then the ring, the cross-sectional area is going to be pi big R squared minus pi little r squared extracted. Okay. So, for example, let's spin this. I'm going to spin this little triangular template from 0 to 3 underneath the curve y. So I have these little triangular plates. And I'm going to spin it around what? This y-axis. Y-axis, y, and I mean y to minus 2, horizontal axis. So as it spins, it's going to form the following shapes. Okay. And now I'm going to slice it across the axles of spinning, which each slice is a ring. Okay. Now, in particular, what I want is at a particular x, given an x, so the x from 0 to 3 at x. What is the big radius versus what is the little radius of that ring at a given x? Well, at a given x, so this is where you have to look at a given x over here, what is from here to here? The vertical distance, the top point the top y subtract the bottom, the x minus or minus 2, okay? Or in other words, x plus 2. Outside the big radius is x minus or minus, in other words, from here to here is x, okay? Coordinate, and the y coordinate is x, and here the y coordinate is minus 2. Okay, so it's going to be x top one minus a minus 2. That's why it's x plus 2. That's the big radius. The little radius is just little to go to constant 2. So this is pi big R square minus little r square, and the rest is just calculations. You expand these, you integrate it out, and you plug in the numbers. Okay. Now let's do the other way. That type 2, right? So the boundary line. Now I want the distance, horizontal distance. I spin around y-axis, x or x equal to a constant. Okay. Same thing as before. If I know the x equal to f of y from A to B, then as it spin around the y-axis, then it form a disk. And so, I want to know the radius of this disk. I need the x. Remember, this will be the point x, y. So I want the x variable, the x coordinate, in particular, I want x in terms of some sort of functions in y, because this is based on y. A given y, I need to know the horizontal x in the formula of y. Okay. If I know that, then that area, radius is f of y, and then the disk is going to be pi r squared again. This is going to be pi f of y squared. So therefore, the volume of this by spinning around type 2, this is the formula for it. Okay. Now, suppose I spin this shape away from y-axis, then there's a hole in the middle. Then I will take the big radius, which is this one. This is going to be r, and the little radius is the inside part. And again, it will be pi big R squared or f squared minus a little r squared will be g squared. Okay. So, for example, I have here a piece of the curve y equal to 1 over x squared. Okay, so the y to 1 over x squared, it keeps going down, but I only want this part. Y go from 1, this is 0.11, that point y go to 4, 1/2. Okay. So, but we don't need that. Okay. At a particular level y, what is, as we spin, we're going to spin around the y-axis, so it's going to form a solid look like this, with a hole in the middle. Okay, right, where the thing drills out, with the thing solid slopes on the side, and the cross sections of these is going to be a ring, a washer. And the outside big radius, x equal to y minus 1/2, all the way to outside. The inside radius is only up to minus 1/2 to 0. This is the y-axis. This is actually 0. Okay. So minus 1/2. It becomes plus 1/2. Okay. So this is y minus 1/2 minus 1/2. These are the x coordinate at y. So these are given the y level. The x coordinate of this point is y to the minus 1/2, and the x coordinate of this is 1/2, minus 1/2. You subtract the right hand x minus left hand x. Remember, in terms of y. And that's then the rest is just calculate out. Okay, so these are the basic of volume of revolutions. Bye bye. Until next time. Bye bye.